Hi, welcome all for this continued session of UV spectroscopy. And today I'll be talking about the Woodward-Fieser rules, wherein which this kind of set of rules are used to calculate the absorption maxima. And we will be going through certain examples, and there will be some tasks for you guys so that we can use this set of rules and calculate the absorption maxima of any given compound. So first we will understand what for this Woodward-Fieser rules were framed and what is the usefulness of this set of rules. So in order to calculate the absorption maxima or the lambda max theoretically, a person by name Woodward in the year 1941, he actually framed a certain set of rules, and that set of rules or those set of rules were actually the basic observation about a set of observation or absorption spectra for a large number of compounds. And after observation of this set of spectra for a very large number of molecules, he framed certain rules, and he was surprised to see that those set of rules were possibly helping him to calculate the lambda max or absorption maxima for any given structure of molecule. And in the year 1959, a person by name Scott and Louis Frederick Fisher modified these rules with more experimental data, or basically it was a sort of extrapolation of the rules of what the Woodward actually framed. These two people did extrapolation of the set of rules those were framed by Woodward, and they modified the rules, and they were later known as Woodward-Fieser rules. So all these set of rules are used to calculate the position of absorption maxima for a given structure by relating the position of lambda max with the position and degree of substitution on the chromophore. So what they did was they observed a set of molecules and they studied their structure, and they added certain values for those structure, and they calculated the theoretical value of this absorption maxima. I have already defined what is absorption maxima. Absorption maxima is the wavelength at which the maximum absorption takes place. That is known as absorption maxima, and it is also termed as lambda max. The longer the conjugated system, so why is the conjugated system involved here? Since the conjugated system is having a lot of double bonds, and these double bonds are the one which are responsible for pi to pi star transitions. The longer the conjugated system, the greater the wavelength of absorption maxima. So we are adding a lot of contribution to the electronic character of a molecule, and that in turn will lead to the increase in the absorption or shift in the wavelength towards the longer wavelength region. The intensity of absorption also increases with increase in the length of chromophore. So we had studied all the 4 different kinds of shifts in the previous sessions or the previous episodes. I request you to go through those episodes so that we can understand the shift of the wavelength either towards the longer wavelength or either towards the shorter wavelength, or increase in intensity or the decrease in the intensity of the absorption maxima. So the intensity of the absorption also increases with increase in the chromophoric additions that we already have studied. So this set of rules are used to calculate the wavelength of maximum absorption of a compound in the ultraviolet visible spectrum, and has been called as Woodward-Fieser rules or Woodward's rules. And these observations or theoretical calculation of lambda max for any given molecule may differ from the observed or the practical results, and they may vary up till 4 to 5 nanometers, and even sometimes they may vary up till 10 or even more than 10 nanometers. So it is roughly an idea to calculate theoretically the absorption maxima value by using this Woodward-Fieser rules. So we will encounter certain terms in the discussion. So we encounter across dienes, acyclic dienes, and there are few more terms which we encounter. So I will discuss these terms before we go any further. Diene or dienes is a covalent compound that contain two double bonds usually among the carbon atoms. So diene is something which is having two double bonds among the carbon atoms. So with that definition, we have three different types of dienes. The first one is isolated diene, the second one is conjugated diene, and the third one is accumulated diene. The isolated diene, it is a system where two double bonds are separated by more than two single bonds. I'll repeat, it is an isolated diene where two double bonds are separated by more than two single bonds. I have represented these double bonds in red color so that they can be differentiated. They are termed as isolated dienes. Coming to conjugated diene, conjugated dienes are a set of molecules or kind of molecules where the two double bonds are separated by one single bond. Okay, and they are termed as conjugated diene. And cumulated dienes are a set of dienes where the two double bonds are attached to one single carbon atom. Okay, or there is no single bonds between these two double bonds. Those kind of molecules we call them as cumulated dienes. Coming to another term which we come across quite frequently in this discussion, that is acyclic dienes. These are the dienes contained in an open chain system. Okay, these are the dienes that are contained in the open chain system where basic unit is butadiene. Okay, you can see the two double bonds are involved in an open chain system, not in a closed system. We call them as acyclic dienes. Coming to the next term which we come across quite frequently, called as trienes. These are the compounds which contain three separate carbon to carbon double bonds. Okay, here is an example where there are three double bonds which are separated by a single bond. Okay, so these are the compounds, or these are the three separate carbon to carbon double bonds which are separated by a single bonds. And coming to polyenes, polyenes are polyunsaturated organic compounds that contain at least three alternating double bonds. I hope you understand. Three alternating double bonds, I mean to say one double bond here, alternating one more, and alternating one more. So the molecules which contains at least three alternating double bonds and a single carbon-carbon bonds, they are called as polyenes. I have an example for this called as beta carotene, where we have several number of double bonds which are a sort of conjugated double bonds, and they exist as polyenes. Coming to the next term called as homoannular diene. Homoannular diene is basically a cyclic diene having conjugated double bonds in the same ring. I previously mentioned conjugated dienes are the dienes which are where the two double bonds are separated by one single bond. I want to draw your attention here to this molecule where you can see there are conjugated dienes separated by or two carbon bonds or two double bonds separated by a single bond. So if these double bonds are in the same ring, we call this as homoannular diene. I want to show you one more example where I have taken two rings here, but the difference from this structure to this structure is the double bonds are present within the ring system or within the ring. So we call it as homoannular diene. What if it is outside one ring system or one in each ring system? We'll come to that next. So heteroannular dienes are the next class of dienes where it is again a cyclic diene system in which double bonds that are in conjugation are present in different rings. That was what I was referring here in this example. So I will refer to this particular structure here. There is a double bond here followed by a single bond and followed by a double bond. Since there is a set of double bonds connected by a single bond, I call it as a diene. And since these two double bonds are not in the same ring system, rather they are in a two different set of ring systems, I call them as heteroannular dienes. So what is heteroannular dienes? Heteroannular dienes is a cyclic diene in which the double bonds are in conjugation and are present in different ring systems. I have one more example here where one double bond is in one ring system followed by a single bond and followed by a double bond where that double bond is in another ring system. So if there are a dienes or a conjugated diene where the two double bonds are not in the same ring system, we call it as a heteroannular diene. So is this example. I have highlighted this portion as red in color. So that is a conjugated diene, but the double bonds are not in the same ring system, so it is heteroannular diene. So we have differentiated between the homoannular dienes and the heteroannular dienes. The dienes, if they are present in the same ring system, that is called as homoannular, or if it is a conjugated diene but the double bonds are not present in the same ring system, then we call it as heteroannular diene. Coming to one more term called as endocyclic double bond. It is a double bond that is present inside the ring. We call that double bond as an endocyclic double bond. So I have an example here where the double bond is within the ring system. There is one more possibility that the double bond can be outside the ring system. If it is so, then it is exocyclic double bond. So what we mean by exocyclic double bond? It is a double bond in which one of the doubly bonded atom is a part of the ring system. So I mean to say it is a double bond in which one of the doubly bonded atom, that is this carbon, is a part of this ring system. So if this carbon is a part of ring system and the other carbon is not a part of this ring system, I can call this double bond as an exocyclic double bond. So I have highlighted this portion in red color and I have represented this as an exocyclic double bond. So I have an example here. So there is one double bond inside the ring and the other double bond, or the atom or the carbon atom of this double bond is, one atom is connected to the ring and one atom is not connected to the ring. So according to the previous definition, if this is the case, we call this bond as an exocyclic double bond, and according to this endocyclic double bond definition, this is the endocyclic double bond. So we have now understood what we mean by exocyclic double bond and what is endocyclic double bond. So understanding of these terms is quite important so that we can go further and try to assign the values based on these understandings. So I have a question, a small question, so that just to check what if you have understood or not. I have a molecule here. I want you to guess if it is ring A, what ring is this, or what these double bonds are. So whether it is a homoannular or a heteroannular, or whether this ring A is having any exocyclic double bonds, or if this ring B is having any endocyclic or exocyclic double bonds. So I think hopefully you have guessed it right now. So we have a ring A which has one endocyclic double bond and one exocyclic double bond which is corresponding to this double bond. And with respect to ring B has one endocyclic double bond which is this, and ring B has one exocyclic double bond which is corresponding to this. So after understanding all those terms that are involved in these Woodward-Fieser rules, we shall now proceed for the actual rules. And these actual rules will first take up the rules that have been framed in order to understand or in order to calculate the absorption maxima for the conjugated dienes, trienes or polyenes, etc. So coming to the rules, or the set of Woodward-Fieser rules that are for these conjugated dienes, trienes or polyenes, there are a set of rules which we will go through one by one. So each type of diene or triene system has a certain fixed value at which the absorption takes place. This fixed value is known as the base value or the parent value. So if you choose up any diene or triene system, that kind of system will be having certain fixed value, and that fixed value we call it as either a base value or as either the parent value. So if it is a homoannular diene or if it is a heteroannular diene, those kind of, or acyclic diene or a cyclic diene, those kind of systems will be having certain fixed values. We call them as the parent values or the base values. The contribution made by various alkyl substituents or ring residue. So there is some contribution that is being made by the substituents, some of the alkyl substituents or some of the other substituents which we will also address. Alkyl substituents or the ring residues. What we mean by ring residue? Ring residue is something like all the compounds which have aromatic rings, such as benzene rings. They are called as the ring residues. You will understand the ring residues when we will actually take up the example. So there is some contribution being made by these ring residues and also the alkyl substituents. And also there is some contribution that is being made by the double bond extending conjugation. So what we mean by double bond extending conjugation is that, like we know that the two double bonds separated by the single bond is already conjugated. If a third double bond is separated from one of the original pair of the double bonds by a single bond, the three double bonds represent an extended conjugation or extended conjugated double bonds. So that is what we mean by the double bond extending conjugation. So in short, if I want to say, if there is a diene pair and if there is one additional double bond which is again in conjugation with the existing diene pair, then we call that particular system as, or that particular double bond as, a double bond extending conjugation. And also there is a contribution by this double bond extending conjugation, and there are certain polar groups which also contribute for the Woodward-Fieser calculation. They may be the chlorine, bromine, or the OR groups, or the ester groups, or so on and so forth, are added to the base value. All of these contributions, or the fractional contribution what is being made by all these kind of groups, this contribution is added to the base value or the parent value, so that to obtain the absorption maxima for the particular compound. So longer the conjugated system, greater the wavelength of absorption maxima, because there is a lot of electronic configuration or the electronic cloud that is involved in the molecule. More the electron rich the molecule is, the more the absorption happens, and that more absorption is towards the longer wavelength region. So according to Woodward-Fieser rule, the lambda max of the molecule can be calculated by using this formula. I have formula here as lambda max is equal to the base value or the parent value plus the substituent contributions, any kind of substituent contributions what I have discussed, whether it is the alkyl substituent, whether it is the ring residue, whether it is a double bond extending conjugation or any of the polar groups, whatever, they all fall under this substituent contributions. And if there are any other contributions, altogether, if you sum them up, then that is the theoretical absorption maxima value which we can get. So in these two tables, I will give some values for the base values I was talking about, or the parent values what we assign for a given system. So the parent values and the increments for different substituents will be discussed here in this table A and table B, and that is with respect to the conjugated dienes. So we have 4 different parent values, or altogether 4 different types of parent values. The possibility is the molecule may be a cyclic conjugated diene. I have said acyclic. Acyclic is something where it is not a part of a ring system. Conjugated diene, I have explained this in the terminologies that if a double bond is in conjugation, or if it is separated by a single bond, we say it is a conjugated diene. So if it is an acyclic conjugated diene and a heteroannular conjugated diene. Heteroannular in the sense if one double bond is outside the ring system and one double bond is inside the ring, we call that as a heteroannular conjugated diene. If that is the case, we assign a parent value of 215 nanometers. And the case where a homoannular conjugated diene, we have discussed this. So homoannular is where the double bonds are present in the same ring system. If that is the case, then we assign 253 nanometers. Acyclic trienes, we take 245 nanometer as a base value. If it is a butadiene system or cyclic conjugated dienes, we take 217 nanometers as the base value. The table 2, it describes the increments and their contribution in terms of nanometers. So if for every alkyl substituent or the ring residue, it will be 5 nanometer. For exocyclic double bond, I mentioned what is exocyclic previously. That exocyclic double bond will contribute 5 nanometers. Double bond extending conjugation will contribute very significantly, that is 30 nanometers. And for any of the oxychromes that are present on the system, if it is OR, it contributes 6 nanometer. If the oxychrome is SR, it contributes 30 nanometers. If it is some of the chlorines or bromines, either of these will contribute 5 nanometers each. And if it is NR2, it contributes 60 nanometers. And if it is OCOCH3, then there is no contribution. So with this values from table A and B, we'll try to experiment this set of values by taking some examples. So I have the first exercise now. So I'm asking you to, or we shall first calculate the absorption maxima or lambda max for this particular molecule. We need to analyze this molecule for what it has. So it is a molecule where we have a conjugated diene system, and this conjugated diene system is within the ring. And if you can see the carbons that are involved, or the carbon that are involved in the double bond, one of them is having a substituent and one of the carbon is having a substituent. So we need to look on this very keenly and then come one by one. So I have highlighted these two double bonds. So since these two double bonds are within the ring, I call this as a homoannular diene. So the parent value for homoannular diene we have discussed previously. It is 253 nanometers. This is the parent value or the base value what we have added for this molecule as a whole. Coming to the next substituent, since we are done with the parent value, we need to go for the increments what we have discussed from the table 2 or table B. So from that, the increment, if you see, we have two increments here. The first one is the ring residue and the second one is the alkyl substituents. So let me show you the alkyl substituents. There are two alkyl substituents on this carbon which is involved in the double bond formation, and one alkyl substituent on this carbon atom which is involved in the double bond. So since we have two alkyl substituents, we count them as 2 times 5 nanometer because each of the alkyl substituent will be accounting for 5 nanometer. So we have two alkyl substituents, altogether it sums for 10 nanometer. So after this, I said we need to look for the ring residues. So these are the two ring residues. So how to look for these ring residues? I have already mentioned, since this is a carbon atom which is involved in the double bond formation, any bond that is attached to this carbon atom and that bond is involved in the ring system. I repeat, any carbon that is attached to a double bond or any bond that is attached to this carbon atom and that bond is a part of the ring system, then that bond we call it as a ring residue. So we have how many ring residues? One here, and this carbon atom is having one ring residue here because this single bond is involved or is a part of the ring system. So we have how many? We have two ring residues and each will contribute for 5 nanometers. So altogether we have 2 ring residues contributing 10 nanometers. So is there anything left out? I think nothing has been left out. We have addressed the substituents or the increments. We have addressed the parenting. So altogether, if we sum up these values, we have around 273 nanometer as the calculated value. So this calculated value is nothing but the theoretical calculation by using Woodward-Fieser rule. And if you observe this absorption maxima experimentally, then that becomes the observed value, which is around 265 nanometer. So there is no much difference between the theoretical value and the observed value. Hardly it is 70 and 73, 8 nanometer, which is not that big difference. So that is the advantage of applying this Woodward-Fieser rule, wherein which we can theoretically calculate the absorption maxima value, which can be observed experimentally. So while you are observing experimentally, we should take care of one thing. The value what we get as the absorption maxima in experiment, it depends on the kind of solvent in which this molecule is dissolved into. So that affects this observed value very significantly. That is one thing which we should remember carefully. So with this we'll go for the next exercise, that is exercise number 2. We shall now calculate the lambda max for this particular molecule. On the first site, if you want to see the parent value, if you want to assign the base value, then it looks like it is not a homoannular but it is a heteroannular diene, because each of these double bonds are in a different ring system. So we have seen these 2 double bonds and we came to a conclusion that the parent value is a heteroannular diene. From that particular table number 1, we will assign 215 nanometers for this molecule as a parent value. So we shall now go for look for any increments here. Any alkyl substituents? There are no any alkyl substituents. I can only find some ring residues. So as per the previous definition, any carbon atom that is involved in the double bond, and if that carbon atom is having any single bonds or any bonds that is involved in the formation of the ring. So we have in general how many? 1, 2, which is this particular single bond that is involved in this ring, one more here and one more here. So how many ring residues we have is we have in together 4 ring residues. So I have 5 nanometer for each ring residue and I have 4 ring residues. That is an increment. In total it is 20 nanometer. So there is nothing left out. On adding this, we get 235 nanometer as the calculated value for this particular molecule. So if you observe the absorption maxima experimentally for this particular molecule, then it sums to be 236 nanometer. So as I have mentioned already, the observed value or the experimentation value will depend on the kind of solvent that this molecule is taken into. And here you see there is no much difference between the observed value and the calculated value. Rather, it is only differencing or it is differentiating by 1 nanometer. We shall now take the next exercise wherein which we shall calculate the absorption maxima value for this particular molecule here. And so at first instance, what we are looking out here is a ring system which does not have any double bonds, whereas there is a double bond which is involved in this part of a cyclic structure which is not cyclic in nature, and there is one double bond alternating to one single bond and another double bond, so it is a diene. So I can see some methyl substitutions on this carbon which is involved in the double bond. I can see one methyl substitution on this carbon atom which is involved in a double bond formation. So I have 2 double bonds which is a diene. I have 2 substituents and there is one acyclic system. So what I'm trying to find out is the parent peak the parent value or the base value. So looking onto this structure, it looks like the parent value should be framed on this particular part of the molecule, and since it is the acyclic conjugated diene, I will assign the particular value for this acyclic conjugated diene as 215 nanometer. And after this, as I mentioned, we need to add certain increments for these two methyl groups, which are the alkyl substituents. So we have two alkyl substituents, so 2 times 5 is 10 nanometer. And as I have mentioned previously, if there is a carbon atom which is involved in the double bond, and that carbon atom is a part of a ring system, or if that carbon atom is having any single bonds which is a part of ring system, then we call them as ring residues. So we have two ring residues here, so I should add them as increment. So we'll add them as increment, two ring residues, 5 nanometer each, so it is total 10 nanometers. So I was talking about the bond if it is not within the ring system, but if it is outside the ring system and where one of the carbon atom is involved in the double bond, is attached or is a part of the ring system, then we call that particular carbon as, or that particular double bond as the exocyclic double bond. Say I have mentioned it here. This particular portion I will assign as an increment as an exocyclic double bond, which is 5 nanometer, and there is nothing additional increment left out. So let's sum up all these values to get the calculated value as 240 nanometer, and if you see the observed value, it is the 242 nanometer. So it is not differing much, rather it is differing only by 2 nanometers. So after these three set of exercises, I would like you to take up this task, which is task 1, and I would like you guys to request and take a piece of paper and a pen, so in order to calculate the lambda max value for this particular structure. So I'll just give a hint how to calculate, or what are the things you are supposed to look out for. First, assign the parent value, which in this case I will give it as a hint. It is a homoannular diene, and look for any ring residues or alkyl substituents or any exocyclic double bonds or any double bonds which are extending the conjugation. So this is all the hint I can give up. So I request you to take up this task and report the observed value, as well as, no need to report the observed value because that is quite natural to be obtained from an experimental data. I request you to submit the calculated value for this particular molecule. With that, we'll go for the next section, that is the Woodward-Fieser rules, which have been used to calculate the lambda max for alpha beta unsaturated carbonyl compounds. There are some set of rules or additional set of rules which have been modified by Scott in order to calculate the alpha beta unsaturated carbonyl compound absorption maxima. So the empirical rules that were defined by Woodward and Fieser, they were modified by Scott in order to apply those rules for alpha beta unsaturated compounds and get the absorption or get the absorption maxima values. So these are the two tables where represent the parent values, as well as the next table in the next slide will show you the increment for the substituents. I'll just go through this table. C, alpha beta unsaturated acyclic or 6-membered ring ketone. Why ketone? Because it is an alpha beta unsaturated carbonyl compounds. We are supposed to have a carbonyl molecule. Adjacent to that is a alpha carbon, and adjacent to that is a beta carbon, and there is a double bond between the alpha and beta carbon. So if that is the case, if it is an alpha beta unsaturated acyclic or a 6-membered ring ketone, we need to assign 215 nanometer as a parent value. For alpha beta unsaturated 5-membered ring ketone, we assign 202, and for alpha beta unsaturated aldehyde, we assign 207. These are the parent values. Coming to the increments, that is with respect to the table D, which we have here. So for each alkyl substituent or ring residue, if it is at alpha position, we assign 10 nanometer. Alpha position in the sense, if it is on the alpha carbon atom that is involved in the double bond formation, we assign 10 nanometer. If it is at beta position, we assign 12 nanometer. If it is at gamma position or higher position, we assign 18 nanometer. So any alkyl substituent or ring residue, if they are present in all these three possible positions, we assign all these three possible values. For each exocyclic double bond, we assign 5 nanometer. For double bond extending conjugation, significantly, as like previous, it is 30 nanometers. And homoannular conjugated diene, if it is a homoannular conjugated diene, we assign 39 nanometers. And for oxochromes, we have a set of oxochromes and the position they may occupy in this alpha beta unsaturated compounds. So I request you to memorize these values in order to calculate the absorption maxima values for any given molecules. So with this, we will straight away go for the next exercise, which is exercise number 4, where in which I have a molecule here. I said it is an alpha beta unsaturated carbonyl compound. Since it is a carbonyl molecule here, a carbon adjacent to this carbonyl carbon is an alpha carbon, and there is alpha beta unsaturation here, and this is a beta carbon. So we shall attempt to calculate the absorption maxima for this particular molecule. First, look for the base value. As I have mentioned, it is an alpha beta unsaturated acyclic ketone. Since there is no ring structure here, I will assign a value for that. It is alpha beta unsaturated acyclic ketone, which is having 215 nanometer as a base value. So after that, we are looking for any ring residues or any alkyl substituents. Since there is a no ring involved, the ring residues is absolute. So we have one substitution on this alpha carbon, which is a methyl or an alkyl substitution. So I will assign for this alkyl substitution one increment. So I have 10 nanometer for this. So there is nothing much left out to be assigned as an increment. We shall directly sum it up, which is 225 nanometer as a calculated value, and 220 is an observed value. Again, I would like to mention here that this observed value depends on the kind of solvent this molecule is dissolved in while we are taking the absorption readings. Coming to the next exercise, which is exercise 5, I have a structure here which is an alpha beta unsaturated carbonyl molecule where we have some ring systems, and we will attempt to draw some conclusions about this structure so as to obtain the absorption maxima values. So in order to look the parent value, we have alpha beta unsaturated 6-membered cyclic ketone. We have this 6-membered cyclic ketone. So we shall assign the parent peak as alpha beta unsaturated 6-membered cyclic ketone, which is 215 nanometer. So after that, we need to add the increments, whether it is the ring residue or any alkyl substituents, so on and so forth. So first we will try to look for the ring residues. We have one ring residue at alpha position here. This particular thing I have denoted here as a red dotted line. We have one ring residue because this single bond is a part of this ring system. We have one ring residue here, so one ring residue at alpha position is 10 nanometer. So we have two ring residues on this beta carbon, and for that we assign two ring residues at beta position 12 nanometer each. 12 times 2 is 24 nanometer. And if there are any exocyclic double bonds, I can see some exocyclic double bonds to two rings. If I take this as a ring A, I have one exocyclic double bond here. If I take this as a ring B, I can see one more exocyclic double bond here. So in altogether, I can find two exocyclic double bonds. So I will mention it as double bond exocyclic to two rings, and one exocyclic double bond has 5 nanometer values. Since we have two, it is altogether 10 nanometer. So there is nothing left out to be addressed here, so we will sum it up. So in order to calculate the calculated value, it sums to 259 nanometer, and experimentally if we observe, we get it as 256 nanometer. So there is no much deviation between the calculated and the observed values. We shall now go for the next exercise, wherein which we will try to calculate the absorption maxima for this particular molecule. I have a part of molecule here where this represents an extension of the molecule which I am not interested in. So at first instance, I can see it as an alpha beta unsaturated molecule, which is, there is a carbonyl molecule here. So it is an alpha beta unsaturated molecule. So what I will do is, it is an alpha beta unsaturated 6-membered ring ketone. Okay, so I will assign 215 nanometer and look for the increments here. So the first increment is look for any ring residues. So at this alpha carbon, I can see one ring residue. I cannot take this as a ring residue is because this is involved in, or this particular single bond is attached to this carbonyl carbon. So I cannot take this as a ring residue, rather I will take this as a ring residue. So one ring residue at alpha position is 10 nanometer, and look for any ring residues which are attached to these carbons which are involved in the double bond formation. Yeah, there is one carbon where I can assign a ring residue at delta position, which is 18 nanometer. And after this, I want to look at any exocyclic double bonds. So one exocyclic double bond is this carbonyl, because since it is alpha beta unsaturation, this is an exocyclic double bond to this particular ring. So I have one exocyclic double bond of 5 nanometer, and if this is a double bond what I am interested in, since it is alpha beta unsaturated, I have one double bond which is a homoannular kind, and this I will assign it as a homoannular conjugated diene. Okay, exocyclic double bond. Okay, let me go for one double bond extending conjugation. So this is alpha beta unsaturated carbonyl compound. This particular gamma and delta, there is an extended conjugation. So I will add one double bond extending conjugation as 30 nanometer, and this whole molecule I can see it as a homoannular conjugated diene because both the double bonds are within the ring. So I call this as a homoannular conjugated diene. I assign the value as 39 nanometers. So if I sum this, I have 317 nanometers and observed is 319. So with this exercise 6, we have next task where I am expecting you guys to calculate the absorption maxima for this particular structure A and particular structure B, and I request you to submit the report for this particular structure A and for this particular structure B. So just some hints for this structure A, wherein which this is again an alpha beta unsaturated acyclic ketone, where you are supposed to look for some alkyl substituents, and there is no question of ring residues here because there is no ring that is attached to these two carbon atoms. That is with respect to structure A. Coming to structure B, we need to assign the parent value, wherein which this is an alpha beta unsaturated 6-membered ring ketone, or 6-membered ring which is attached to this alpha beta unsaturated ketone. And since there is involvement of ring with these two carbon atoms, I expect the ring residues to be calculated, and yeah, that's it. And if there is any substitution on the carbons that are involved, or either on this alpha or in this beta, you are supposed to calculate the values, or you are supposed to assign the increments for those particular values. So these are the two tasks, the task 1 and task 2, which you are supposed to submit and submit as a report. So with this, we are done with the Woodward-Fieser rule, and these are some of the references which I have followed in order to prepare this PowerPoint presentation. So one more important thing before I conclude with this topic is that this Woodward-Fieser rules will be calculated for all the conjugated dienes having less than 4 double bonds. If the double bonds are more than 4, then we have another set of rules, or if the conjugated diene is more than 4, then we have something called as Fisher-Kuhn rules, which I am not going to discuss here in this session. So I expect, if you are going for any further reading, I expect you to go through those Fisher-Kuhn, K-U-H-N, Kuhn rules, so that you can understand the further application of this Fisher-Kuhn rules. So with that, I will be ending with this Woodward-Fieser session. Thank you for being with me so far. Thank you very much.